Welcome back, engineers. So we have covered many of the core concepts in system design, and we have also seen some numbers, we have seen how to do estimation and so on. Now we'll look at some common techniques and algorithms that power our modern day applications, right? So in this video, we're going to start with quad trees, which are used in applications like Uber, Ola, Swiggy and Zomato, where we are looking for spatial search, right? I hope you're ready. Let's get started. So we'll start with the first question. What is a quad tree? Right? So quad tree is a data structure, just like how you would have studied data structures like binary trees, linked lists, stacks, queues, and so on, right? So quad tree is one type of data structure that is efficient in doing spatial search, especially in two-dimensional data, right? So let's see where quad tree is used. First application is where we want to do spatial search. So we want to divide the world map in 2 dimensions and we want to do a search on this particular world map, let's say, right? So let's say I want to find some spot here on the world map. So it is very inefficient to store all the points on the world map, and we want to look for one particular point or one particular area. It is very inefficient to do a linear search, which is of time complexity O of n, right? So what do? We break down this entire search space into smaller blocks, smaller rectangles, and that is where quad trees are used, because it reduces the search space from O of n to generally O of log n, right? So this is where spatial search is used. It is mainly used in applications like Uber, Ola, Swiggy, Zomato, where we are looking for nearby stuff. Let's say who are the nearby drivers to my location, right? So we can use quad trees for that. And we can also look for nearby drivers for restaurant deliveries, right? So in this scenario as well, we can make use of quad trees. The second scenario where we can see the usage of quad trees is in image processing. So let's say we have a face like this, which is represented in a 2D grid. This is also a two-dimensional data, right? So we have an image represented in a 2D space. We have rows and columns, and we have pixels. Every pixel has some RGB color, and together it forms an image of a human face, right? So let's say we want to do some image processing. So we try to break down this image into smaller pieces. Wherever there is a big area where there is no change in color, we can keep it as it is, and wherever there are more colors involved, we can break down the image into more granular pieces so that we get more accuracy from the image and we can do some further processing, right? So in this case as well, we can do quad trees. And the third scenario where we can see quad trees is in gaming. So let's say we have a game space in 2 dimensions and we are doing some physics activities in the game, maybe jumping or fighting with each other and so on. So we want to do some collision detection. We want one character or one piece of the game, when it collides with the other, it needs to do something else, right? So how do we do that? We don't check for the entire search space for every movement of the character. So we try to break down the search space into smaller pieces. Wherever there is need for checking more collisions, we can do more granular breakdown. And the areas where we don't need so much granularity, we can choose not to break it down, right? So in these kind of situations as well, we can see the usage of quad trees. So now let's talk about the time complexity. So let's say we have a simple 2D space like this, A, B, C, D. Let's say this is a 2-dimensional array. So we have 0, 1, 0, 1 as rows and columns. So let's say I'm searching for D, right? So how do we search for D? We start at the first row, first column. We check if this is D. Otherwise, we move to the next column, we move to the next column, and so on until we exhaust this whole row. And then we move on to the next row, and then we do column-wise search again, right? So this is typically O of n operation. But in quad trees, this is how the time complexity changes. Let's say on a worst case, let's say in the worst case, every data point is available here in the far more corner, and there is a big cluster here. And the rest of the space is just empty or let's say sparsely used, right? So in this case, the time complexity goes up to O of n, because we kind of are looking for something across all the points in the map. Let's say we are looking for something in this corner of the world. So we are mainly looking at all the points. So this is a worst case scenario. But in general, the average case would be log n, O of log n, because when we are looking for something in this quad tree, we are only going to the depth that is desired for us and not going beyond that. So when we take a look at the structure and how search works, we'll have a better understanding of this. But for now, just remember that the time complexity is vastly reduced from O of n to O of log n, right? So this is the main introduction about quad trees. Now let's look at some of the fundamental concepts involved with quad trees, right? So let's start by understanding the difference between binary tree versus quad tree, right? So you must have seen binary trees which look something like this. Let's say we have a node here which is the root node. Each node has two other nodes, and those nodes can have further nodes, and these are the leaf nodes, right? So this is how a typical binary tree looks like, right? So every node can have potentially two nodes as its children, right? But you must have seen this and you must be thinking, hey, this is not looking like a tree at all. But it is, in a sense, if you start understanding how a quad tree is constructed, right? So let's say we have a two-dimensional space like this, which is kind of like an entire city, let's say, right? So how do we break down the city? We can break it down into 4 parts like this, and each part is called as a quadrant, right? Each part is a quadrant. Let's say this is quadrant 1, quadrant 2, quadrant 3, quadrant 4, and so on. And we can take this a step lower and break it down further. Let's say we can break down the quadrant 2 into 4 other subparts, right? Let's say this is 2A, 2B, 2C, 2D, and so on, right? And we can break down 2B into 4 other parts, and so on, right? So how is this a tree, right? So if you imagine it, the first node that we had was the entire search space. Let's say this is the entire search space. This is the first node, right? And when we broke it down into 4 parts, we had 4 children, 1, 2, 3, 4, and these were numbered 1, 2, 3, 4, right? And what did we do next? We broke down the second quadrant into 2A, 2B, 2C, 2D. So 2 has 4 other children, 2A, 2B, 2C, and 2D, right? So if you think about it, now you can see the tree structure, right? This looks like a tree. There is a root node has 4 children, and one node can have 4 other children, right? So this is how a quad tree is constructed. So in a binary tree, every node could have a maximum of 2 children. In a quad tree, every node could have a maximum of 4 children. So that is why it is called as a quad tree, right? So this is how a two-dimensional space can be broken down into smaller and smaller pieces depending on the need. So depending on the granularity requirements, we can go deeper and deeper into the tree by breaking down the quadrants into 4 other pieces by going deeper and deeper, right? So this is how spatial decomposition works, and this is how quad tree is broken down into quadrants. Now let's look at the structure and data representation of a quad tree. So this is how a quad tree node typically looks like. So we have a quad tree node and we have the points x, y. These can be the identifiers for this particular quad tree node. So this can be the center of the entire quadrant, or this can be the top left corner, like this. So this can be xy or this can be xy. We only need one of the points to determine the entire quadrant, because next we will have width and height, right? So once we have the origin, we have the width and height, we know the entire search space for that quadrant, right? And then we have the data. Data can be anything. It can be binary, it can be the list of drivers, it can be the list of restaurants, and so on, right? And then we have the children. So each quad tree node can have up to 4 children. We have top left, top right, bottom left, and bottom right as the children, right? So this can be used in different notations. Some people call it northwest, northeast, southwest, southeast, or we can call it top left, top right, bottom left, and bottom right, right? So depending on the need, these are initially null, and if the quadrant is to be broken down to a further granular level, we can create 4 other children and attach them to the parent, right? And finally, we have another flag to indicate whether this is a leaf node or a divided node. So let's say we have the structure like this. So in this case, we can see that this node does not have any further children, so this is a leaf node, and this one has further children, so this is not a leaf node, which means that we can go deeper into the search space with this one, right? So this is how a quad tree is constructed, and that's the difference between a leaf node and a divided node. And we can also have a reference to a parent node like this, just in case we want to go up the search space, right? So we can go down the search space by using these children, but let's say we want to go up the ladder, we can use a parent node to climb back up and look for the siblings in that level, right? So we can also do that. Now let's look at the construction of a quad tree. So quad tree is constructed using recursive subdivision, right? So because it is a tree, we can use depth for search or depth for traversal to do recursive subdivision as needed, right? So we start with the initial search grid, which is an empty 2D space, and we can do the first division into 4 quadrants like this, and we can do the next division into 4 quadrants like this, and we can go deeper and deeper as we want, and this is a recursive operation. So depending on some criteria, we make the decision whether to divide it or not. So what will be the decision? There can be many such ideas like this. Let's say quadrant has more than n points. Let's say I want each quadrant to have, let's say, only one driver. So let's say if there is one driver here, there is one driver here. So as soon as there is a new driver involved in this quadrant, right? So we break it down. We break it down into 4 other pieces. Now each quadrant has only one driver. So let's say that is our criteria. Another criteria can be tree max depth is not met. So we can go up to the maximum depth allowed for the tree. We can keep on subdividing, right? Let's say granularity is not met. So we're not happy with the current granularity. Let's say I've broken down the city into different pin codes. Let's say I'm not happy with that. I want to achieve more accuracy. So I break it down at a kilometer level or maybe at a meter level, right? So that is how granularity can be managed depending on the need. So depending on any of these criteria, the division can happen dynamically. So now let's see how the operations happen: insert, delete, and search. So first let's look at insert, and let's say we are Uber and we are planning a city, right? Let's say this is our city and this is the entire city, right? Let's say our first driver has entered the scene. There's a new driver registered in this corner, right? Let's say our criteria is to have one driver per quadrant. So what do we do? Because this is the first driver entered, this space is okay. One driver is allowed in this space. As soon as the next driver is registered, we break down this space into 4 quadrants. So whenever a new driver is added, we break it down into 4 quadrants. So now each quadrant has just one driver, which is our requirement. As soon as the second driver is added here, we can break this down further. So this is how insert works. Now let's see how delete works. Delete is nothing but like a cleanup job. Now let's say this driver is no longer with us. Let's say this driver has unregistered. Now we can check the siblings. Are there any other drivers in the entire 4 siblings? There is only one driver in the entire quadrant with 4 quadrants. Entire 4 quadrants. So what we can do? We can do merge of these and we can remove the other quadrant so that we can save our search space, right? So we can just look for this driver in this space instead of going down one level down, right? So that's how delete works. So how does search work? Search works like this. So this is how search works. Search uses a top-down approach, right? So we start at the root node and we check the boundary of the root node. So the input to this search space is, let's say, one point in the search space, one row column or one lat long, right? So we check whether the root node is fitting this boundary. If yes, then we check if the root node has any children. If there are any children, we check if any of the child can fit the point that we are looking for, the boundaries of each of the child nodes. And if it works, then we go into that particular child and then repeat this operation until we are at a level where no further subdivision is possible, right? So that is how recursive search works. So this is using a depth first search pattern basically. And now let's see finally nearest neighbor search. So how do we do this? So we use search first to reach to the quadrant where the point is located, and we look for other points in that search space, right? So let's say we have reached until this quadrant. We are looking for other points in this search space, right? If you're happy with it, we can keep it. Otherwise, if you want to add more area to the search space, we go up the ladder now and we increase the search space, let's say to this, right? So that is how nearest neighbor search works, at least in the general theoretical sense, right? So this is how the operations in a quad tree works. Now let's finally look at some limitations and alternatives to quad trees. So as always, nothing is a foolproof solution. Everything has some limitation. So for quad trees, we cannot use it when the data is very highly dynamic. So if your data is constantly changing and constantly need to be adapted, then quad tree may not be the optimal solution for this. And this is also not ideal when we have non-uniform data. Let's say all our points are clustered in one particular corner. We are not getting any efficiency out of quad trees, so we may not choose to use quad trees in that sense, right? And this is also the case where we have very sparse data, right? So extreme corners where the data is very sparse or very dense, quad trees may not be very efficient because eventually we are looking at every search point, right? And these are some of the alternatives to quad trees. We can use KD trees and R trees if the data is multi-dimensional, more than 2 dimensions, let's say. So have a look at these trees as well when you are implementing or when you're discussing quad trees, right? So this was a brief introduction about queries, guys. I hope you got some basic understanding about what is a query and how it works. So in the next video, we'll try to cover another common technique. So until then, thank you so much for watching. Please leave a like if you found this helpful. Please subscribe if you haven't done already. I will see you in the next video. Cheers.